Hi students, in this video we are going to talk about limit theorems. The most important theoretical results in probability theory are law of large numbers and central limit theorem. Law of large numbers states the conditions under which the average of sequence of random variables converges in some sense to expected average. On the other hand, central limit theorem concerned with determining conditions under which the sum of large number of random variables has a probability distribution that is approximately normal. Before we see these results, we need to understand different modes of convergence for sequence of random variables. Okay? The first mode of convergence that we are going to see is convergence in probability. Let me give a definition here. Let x n be a sequence of random variables and x is another random variable, all depend on same probability space omega script of p. We say xn converges in probability to x if for given any epsilon greater than 0, the limit of the probability of mod xn minus x greater than or equal to epsilon equal to 0 as n go to infinity. Okay. Here for each n we have one probability. For example, n equal to 1, the probability of an event that we got, let us say p1. For n equal to, the probability of event that we get is p2 and so on, let us say. Now we have the sequence of real numbers. As a sequence of real numbers, this should approach as 0 as n go to infinity. Then we say xn converges in probability to x. Equivalently, we can also say like this. Limit of probability of mod xn minus x less than epsilon equal to 1 as n go to infinity. Okay. If xn converges in probability to x, we write like this and we read it as xn converges to x in probability. Okay. Fine. Here is an example. Let xn be a sequence of random variables. Here each xn take the value 1 or 0. Here xn take the value 1 with a probability 1 by n, 0 with a probability 1 minus 1 by n for n equal to 1, 2, 3, so on. I am going to show that xn converges to 0 in probability. Here 0 means degenerate random variable at 0. Okay, fine. For that, I need to show for given epsilon greater than 0, the limit of the probability of mod xn minus 0 greater than or equal to epsilon equal to 0 as n go to infinity. Okay, let me consider this event, the probability of mod xn minus 0 greater than or equal to epsilon. That means probability of mod xn greater than or equal to epsilon. If epsilon greater than 1, this event going to be impossible because xn can take either 1 or 0. So mod xn can never be something more than 1. So this is going to be impossible. In that case, the probability of this event will be 0. If 0 less than epsilon less than or equal to 1, then this mod xn greater than or equal to epsilon will be equivalent to xn equal to 1. Okay, so that's why the probability of mod xn greater than or equal to epsilon will be same as the probability of xn equal to 1, which is 1 by n. In either case, this will be approaching 0 as n go to infinity. So the probability of mod xn minus 0 greater than or equal to epsilon go to 0 as n go to infinity. Okay, therefore we can say xn converges to 0 in probability. Here 0 means degenerate random variable at 0. Fine. Okay. The next mode of convergence that we are going to see is almost sure convergence. Okay. Definition. Let xn be a sequence of random variables and x is another random variable, all depend on same probability space omega script of p. We say xn converges almost surely to x if the probability of an event consisting of outcomes omega in the sample space for which limit of xn omega equal to x omega is 1. See, For every outcome omega in the sample space, we have a sequence of real numbers, that is x1 omega, x2 omega, so on, xn omega. This is a sequence of real numbers. As a sequence of real numbers, if this sequence converges to real number x omega, then we write like limit of x1 omega equal to x omega as n tends to infinity. If this happens almost every outcome in the sample space, then we say xn converges almost surely to x. What do you mean by almost every outcome in the sample space? That means probability of an event consisting of an outcome for which this happens should be equal to 1. Okay, that's by this definition. Okay, this is equivalent to, I can also write like the probability of an event consisting of outcomes in the sample space for which limit xn of omega not equal to x omega. This probability is 0. Then also we can say xn converges almost surely to x. Okay, this convergence we write in the following way, this way or this way. Okay, this one we read it as xn converges to x almost surely. This one we read it as xn converges to x with probability 1. Okay, actually this almost sure convergence stronger than convergence in probability. Next I am going to show that almost sure convergence implies convergence in probability. Okay, fine. Note, xn converges to x almost surely implies xn converges to x in probability. Okay, first of all, what is the meaning of xn converges to x almost surely? Which means the probability of an event consisting of outcomes omega in the sample space for which limit of xn of omega equal to x omega is 1. Okay, equivalently we can say the probability of an event consisting of outcomes omega in the sample space for which limit of xn of omega not equal to x omega is 0. Okay, fine. Now I want to show xn converges to x in probability. For that, I need to show for given epsilon greater than 0, the probability of mod xn minus x greater than or equal to epsilon. This probability sequence go to 0 as n go to infinity. I need to show this. Fine. Okay. Now for given epsilon greater than 0, let me consider this event an, which is the union of these events mod xm minus x greater than or equal to epsilon. If this union runs over m, which is greater than or equal to n. So here for example a1 is what? Mod x1 minus x greater than or equal to epsilon union mod x2 minus x greater than or equal to epsilon union mod x3 minus x greater than or equal to epsilon union and so on. So what will be a2? Mod x2 minus x greater than or equal to epsilon union mod x3 minus x greater than or equal to epsilon union and so on. As you can see, a1 contains a2, then a2 will contain a3 and so on. So here we have a decreasing sequence of events. Here an is decreasing. Here an contains an plus 1, then an plus 1 contains an plus 2 and so on. Okay, so here an is decreasing sequence of events, and limit an is a notation for intersection of this an where this intersection runs over n greater than or equal to 1, which is going to be subset of this event consisting of outcomes omega in the sample space for which limit of xn of omega not equal to x omega, because if any outcome sitting in this intersection an for all n greater than or equal to 1 means what? Mod xn of omega minus x omega greater than or equal to epsilon for all n. If this is the case, then xn of omega cannot converge to x omega. So we have this limit of xn of omega not equal to x omega. Okay, that's why that omega also sitting in this event. Okay, and we know that the probability of this event is 0. Okay, now limit of probability of an using the continuity of the probability, I can write probability of limit an, and here limit an is a subset of this event, so the probability of limit an will be less than or equal to probability of this event, and this probability is 0, so I can say that limit of the probability of an is 0. Okay, now this event mod xn minus x greater than or equal to epsilon subset of an, because here an is what? Union of mod xm minus x greater than or equal to epsilon, here m greater than or equal to n. As you can see, this event is one member in this union, that's why this event is subset of an. So we have this probability of mod xn minus x greater than or equal to epsilon less than or equal to probability of an, and we know that this limit of the probability of an is 0. So this probability of an go to 0 as n go to infinity. So we can say that probability of mod xn minus x greater than or equal to epsilon go to 0 as n go to infinity. Hence we can say xn converges to x in probability. Fine. So almost sure convergence implies convergence in probability. But converse is not true. Next we are going to see counterexample. Okay? Fine. Now I am going to construct sequence of random variables for which we will have a convergence in probability, but we will not have almost sure convergence. Okay? First of all, for each positive integer n, there exist integers m and k uniquely such that n equal to 2 to the power of k plus m, where 0 less than or equal to m less than 2 to the power of k. Here k can be anything from 0, 1, 2, 3, so on. Okay. For given positive integer n, this m and k are uniquely determined. Okay. For example, if you take n equal to 1, then k equal to 0, m equal to 0. If you take n equal to 7, then k equal to 2, m equal to 3, so on. Okay. Fine. Now, let me consider the random experiment of picking a number in the interval 0, 1. Then our sample space omega going to be interval 0, 1. Okay. Now let me define random variables xn for n equal to 1, 2, 3, so on. Here xn is a function from omega to r. Okay. Here xn can take either 0 or 2 power k like this. Okay. Xn of omega going to be 2 to the power of k if that omega come from interval m by 2 power k to m plus 1 by 2 power k, otherwise 0. Okay, this m and k are determined with this relation. Fine. Okay, so this is how we are defining sequence of random variables xn for n equal to 1 to so on. Okay, fine. Here the probability of xn taking the value 2 power k will be equal to length of the interval m by 2 to the power of k to m plus 1 by 2 to the power of k, which is 1 by 2 to the power of k, because xn take the value 2 to the power of k if and only if outcome come from this interval. That's why the probability of xn equal to 2 to the power of k should be equal to length of the interval, which is 1 by 2 to the power of k. Fine. Okay. Now I am going to show that xn converges to 0 in probability. For that, for given epsilon greater than 0, I need to show the probability of mod xn minus 0 greater than or equal to epsilon go to 0 as n go to infinity. Okay, fine. Here 0 is the degenerate random variable at 0. Okay. Now let me consider the probability of mod xn minus 0 greater than or equal to epsilon, which is same as the probability of mod xn greater than or equal to epsilon. If epsilon greater than 2 to the power of k, then this event will be impossible event, because xn can take either 0 or 2 to the power of k. So mod xn can never take the value something bigger than 2 to the power of k. So this will be impossible event. in that case the probability will be 0. Okay, if epsilon less than or equal to the power of k, then this event mod xn greater than or equal to epsilon will be equivalent to xn equal to 2 to the power of k, because here xn can take either 0 or 2 to the power of k. Since mod xn greater than or equal to epsilon means xn cannot be 0, the only option is xn must be equal to 2 to the power of k. That's why the probability of mod xn greater than or equal to epsilon will be equal to probability of xn equal to 2 to the power of k, which equal to 1 by 2 to the power of k. Okay, so now in either case this probability will go to 0 as n go to infinity, because here n equal to what? 2 to the power of k plus m, where 0 less than or equal to m less than 2 to the power of k. If n go to infinity, then k also go to infinity. That's why this 1 by 2 to the power of k will approach 0 as n go to infinity, because as n go to infinity, k also go to infinity. So that's why we can say this probability of mod xn minus 0 greater than or equal to epsilon go to 0 as n go to infinity. Hence k go to infinity, right? Hence we can say xn converges to 0 in probability. Okay, fine. But limit xn omega does not exist for any outcome omega in the sample space, because for any outcome omega in the sample space, if you consider the sequence xn omega, x2 omega, and so on, xn omega, in this sequence you will see that there will be infinitely many terms that are 0 and infinitely many terms that are powers of 2. Okay, so this sequence cannot converge to anything. Okay, that's why this xn does not converge almost surely to anything. Okay, fine. Often the limits of the random variables are some constants. For example, if the limit of the random variable is constant a, you have to understand the limit x as a degenerate random variable at a. Okay, so in this case, if convergence in probability, you can simply write xn converges to a in probability. If almost sure convergence, then you can write xn converges to a almost surely. Okay, here you have to understand this a as a degenerate random variable at a. Fine. Okay, next we are going to look at law of large numbers. Law of large number comes in two flavors. One is weak law of large numbers, other one is strong law of large numbers. In weak law of large numbers, we use weak mode of convergence, that is convergence in probability. In strong law of large numbers, we use strong mode of convergence, that is almost sure convergence. Okay. First, let me state and prove weak law of large numbers. Okay. Weak law of large numbers. Here is a statement. Let xn be a sequence of IID random variables having the common mean mu. Then the sample mean xn bar converges to mu in probability. Here xn bar is 1 by n summation I equal to 1 to n xi. What it says is the following. If x1, x2, so on, xn be random sample of size n from the population with a mean mu, then sample mean 1 by n summation I equal to 1 to n xi converges to population mean in probability. It's very intuitive result. Okay, so the sample mean will be better estimate for the population mean as we increase the size of the random sample. Okay, let me prove this. To prove this, what we need to do, for given epsilon greater than 0, we need to show that probability of mod xn bar minus mu greater than or equal to epsilon go to 0 as n go to infinity. Fine? Okay. We are going to prove this result under one additional assumption, that is these random variables having finite variance, so that the proof will be easy. Okay. First of all, we know that this expectation of xn bar will be mu, because expectation of what is xn bar? 1 by n summation I equal to 1 to n xi. By using linear property of expectation, I can write 1 by n of summation I equal to 1 to n expectation xi, and expectation xi going to be mu for each I because they are IID random variables. So it's going to be 1 by n times n mu, that is mu. So expectation of xn bar is mu. Okay. Now the variance of xn bar, that is what? Variance of 1 by n summation I equal to 1 to n xi. First of all, if I bring 1 by n out, 1 by n square come out, and variance of summation I equal to 1 to n xi. And since x1, x2, xn are independent, so variance of the summation xi going to be sum of the variances. Okay, and each of these variance equal to sigma square. So we have 1 by n square times n sigma square. So n the square will go sigma square by n. So this variance of xn bar is sigma square by n. Okay. So here expectation xn bar is mu and the variance of xn bar equal to sigma square by n. Okay. Now for given epsilon greater than 0, using Chebyshev's inequality, I can write that probability of mod xn bar minus mu greater than or equal to epsilon less than or equal to variance of xn bar by epsilon square. Okay, using Chebyshev's inequality. What is the variance of xn bar we got? Sigma square by n. So the right hand side we have sigma square by n epsilon square. This go to 0 as n go to infinity. Okay, so we can say that this xn bar converges to mu in probability. Fine. Okay. Next, strong law of large numbers. The statement will be similar. Only thing is the mode of convergence changed to almost sure convergence. Okay. Here is the statement. Let xn be a sequence of IID random variables having the common mean mu. Then the sample mean xn bar converges to mu almost surely. Okay, fine. This is the statement. We will not prove it here. Okay. Let me show you application of strong law of large numbers. Here I am going to make sense of relative frequency definition of probability. Suppose that a sequence of independent trials of some random experiment is performed. Let E be the event of interest. Then define a sequence of indicator random variables of an event E like this. Xi equal to 1 if E occurs on ith trial, 0 if E does not occur on ith trial, for I equal to 1, 2, 3 and so on. Then expectation of xi going to be 1 times probability of xi equal to 1 plus 0 times probability of xi equal to 0. So this will be probability of xi equal to 1. Xi take the value 1 if and only if E occurs. So the probability of xi equal to 1 will be equal to probability of E for I equal to 1, 2, 3 so on. Okay. Here x1, x2, x3 so on xn are IID random variables with a mean mu equal to probability of E. Okay. By strong law of large numbers, we can say that this 1 by n summation I equal to 1 to n xi converges to probability of E almost surely. We can also say like a with probability 1. With probability 1. Okay. Fine. So now the relative frequency of an event E, that is Fn of E by n, we can also express like 1 by n of summation I equal to 1 to n xi, because this Fn of E will be exactly equal to summation I equal to 1 to n xi. Okay. Therefore, we can say that this relative frequency Fn of E by n converges to probability of E with probability 1. Hence, the relative frequency definition of the probability that we discussed in the beginning actually make very good sense here, right? Fine. Next, we are going to talk about another mode of convergence, that is convergence in distribution. Fine. Definition: let xn be a sequence of random variables and let x be another random variable, all depend on same probability space omega script fp. We say that xn converges in distribution to x if limit n tends to infinity fxn of x equal to fx of x for all x belongs to R at which the CDF of x is continuous. Okay, this convergence we write like this and we read it as xn converges to x in distribution. Fine. Okay, here is the theorem. Let xn be a sequence of random variables with the mgf mxn of t exist for all t in the interval minus h to h for all n. Let x be a random variable with the mgf mx of t exist for all t in the interval minus h1 to h1, where the interval minus h1 to h1 is contained in interval minus h to h. If limit mxn of t equal to mx of t for t in the interval minus h1 to h1, then xn converges to x in distribution. Okay, so it is enough to show that limit of mxn of t equal to mx of t if you want to prove xn converges to x in distribution. Okay, next I am going to prove central limit theorem with the help of this theorem. Fine. Central limit theorem. Here is the statement. Let xn be a sequence of IID random variables that has a mean mu and variance sigma square, then root n of xn bar minus mu by sigma converges to z in distribution where z is a standard normal random variable. Or equivalently, we can also say like this. Summation I equal to 1 to n xi minus n mu by root n sigma converges to z in distribution where z is a standard normal random variable. Okay. Why this is equivalent to this one? Because xn bar is what? 1 by n summation I equal to 1 to n xi, right? So this root n of xn bar I am writing 1 by n summation I equal to 1 to n xi minus mu by sigma. Okay, let me rewrite root n of summation I equal to 1 to n xi minus n mu by n sigma. Again this root n, this n cancel and root n, so we have this summation I equal to 1 to n xi minus n mu by root n sigma. Okay, that's why this one is equivalent to this one. Okay, so to show this, it is enough to show this converges to z in distribution where z is the standard normal random variable. Fine. Okay, we are going to prove it assuming mgf of xn exists for all n. Okay, so let Sn equal to summation I equal to 1 to n xi minus n mu by sigma. This we can rewrite as summation I equal to 1 to n xi minus mu by sigma. Okay, fine. Now let me make a new random variables yi which is equal to xi minus mu by sigma for I equal to 1, 2, 3, so on. Here x1, x2, xn are IID random variables with a mean mu and variance sigma square. So this y1, y2, yn going to be IID random variables with a mean 0 and variance 1. So this new sequence yn be a sequence of IID random variables with a mean 0 and variance 1. Okay, fine. So Sn is what? Summation I equal to 1 to n xi minus mu by sigma. So in terms of yi's, I can write summation I equal to 1 to n yi. So Sn we can write summation I equal to 1 to n yi. Okay. Now the summation I equal to 1 to n xi minus nu by root n sigma, I can write Sn by root n, because what is Sn? Summation I equal to 1 to n xi minus nu by sigma, right? That's why this we can write as Sn by root n. Actually, what we need to show? We need to show summation I equal to 1 to n xi minus mu by root n sigma converges to z in distribution, right? Where z is a standard normal random variable. So it is enough to show this Sn by root n converges to z in distribution, where z is a standard normal random variable. To show this, what we do, we are going to show that mgf of Sn by root n at t converges to mgf of z at t. What is the mgf of standard normal random variable? Which is e power t square by 2. Okay. So again, to show this, what we are going to do, we are going to show that limit of logarithm of mgf of Sn by root n at t, we will show this is t square by 2. Okay. If you can show this, then you can conclude this. From that we can say Sn by root n converges to z in distribution. Fine. Okay. Let me consider mgf of Sn by root n at t. This we can write as mgf of Sn at t by root n. The reason is this. mgf of ax at t, we can write mgf of x at at. Fine? Okay. What is Sn actually? Sn equal to summation I equal to 1 to n. Why I write? Now the mgf of summation I equal to 1 to n y at t by root n, I can write the product of mgfs of my at t by root n from I equal to 1 to n. The reason is this. We have one result that when x1, x2, so on, xn are independent, the mgf of summation I equal to 1 to n xi at t going to be product of mgfs of xi at t product from 1 to n. Okay, so that's why this mgf of Sn at t by root n, actually we can write product of mgfs of y at t by root n is product from I equal to 1 to n, since y1, y2, yn are independent. Also, these y's are identically distributed, so all are going to have a same mgf. Let me call it m of t. If I replace each my of t by root n with a common m of t by root n, so this product going to be m of t by root n all to the power of n. Okay, fine. Now what we have here, the mgf of Sn by root n at t equal to m of t by root n all to the power of n. Okay, now let me take logarithm both sides with a base e. So the logarithm of mgf of Sn by root n at t equal to the right hand side, I can write as n times log of m of t by root n. Okay, now I want to show this limit going to be t square by 2, right? Okay, now this right hand side I am going to write first of all logarithm of m of t by root n by 1 by n. Okay, now I want to show, so we want to show the limit of this right hand side t square by 2. That's our goal, right? See, so first of all, so the right hand side limit I'm writing as logarithm of m of t by root n by 1 by n. Okay, so let's focus on the right hand side. Let me make a substitution y equal to 1 by root n, then y go to 0 if and only if n go to infinity. So if I write the right hand side limit in terms of y, it's going to be limit y tends to 0, I am replacing 1 by root n with a y. So log m of ty by this 1 by n I can write y square. So the right hand side limit I am writing as limit y tends to 0 log of m of ty by y square. Fine? Okay. Now you see the right hand side, it is in 0 by 0 form because m of 0 is what? Expectation of e power 0, that is 1. So the log 1 will be 0. So 0 by 0. So we have 0 by 0 form. So let me apply L'Hopital rule. So to get this limit, what we do? First we differentiate the numerator and denominator. So the derivative of the numerator is going to be 1 by m of ty. By chain rule, we need to differentiate m of ty. That's going to be m dash ty. Again by chain rule, we need to differentiate ty. So it's going to be t because we are differentiating with respect to y. And the derivative of the y square is going to be 2y. Fine? So fine. Now, if I write this t by 2 outside, okay, I can write t by 2 and limit of 1 by m of ty. Okay. Then we have a limit of m dash ty by y. Okay. For a continuous function, finding limits is easy. That is, if f of x is continuous at a, then limit x tends to a, f of x is simply going to be f of a, right? Here mgf is differentiable, so it is continuous. So to find this limit y tends to 0, 1 by m of ty, we simply substitute y equals 0. So we will have 1 by m of 0. So it's going to be 1 by 1. So that is 1. So anyway, this limit is going to be 1 by 1. Fine. And again, to find this limit, again we are going to apply L'Hopital rule because again it is in 0 by 0 form, because m dash 0 going to be what? Is expectation of yi. What is the expectation of yi? That is 0. Okay, so that's why we have a 0 by 0 form. So again we differentiate numerator and denominator. So this anyway we got t by 2, 1 by m of 0, and to find this limit again we differentiated the numerator and denominator. So the numerator derivative going to be m double dash ty. By chain rule again we have this t here, and the derivative of y going to be 1. Okay, now again m of 0 value 1. So here we have a t by 2 times 1, and again this t if I write here, so you will have a t square by 2 times 1 by 1. Here we know that mgf is infinitely many times differentiable. So this m double dash will be again differentiable. So it will be continuous. So to find out this limit, we simply substitute y equals 0. That's why here we have m double dash 0. But what is m double dash 0? Which is expectation of yi square. That's going to be same as variance of yi because expectation of yi is 0. So variance of yi, that is 1. So that's why this value is going to be 1. So what we have here, t square by 2 times 1. So we have t square by 2. What is this? Limit of n tends to infinity logarithm of with the base e m Sn by root n at t equal to t square by 2. That implies we can say limit n tends to infinity mgf of Sn by root n at t equal to e power t square by 2. Fine? So done. Okay? So that's what we wanted to show. So we can say that Sn by root n converges to z in distribution where z is a standard normal random variable. So we have this. Root n of xn bar minus mu by sigma converges to z in distribution where z is a standard normal random variable. Fine. Corollary. Let xn be a sequence of IID random variables that has a mean mu and variance sigma square. Then summation I equal to 1 to n xi will be approximately normal with a mean parameter n mu and the variance parameter n sigma square for large n. In the context of central limit theorem, large means n greater than or equal to 30. Okay. From central limit theorem, we can see that summation I equal to 1 to n xi minus n mu by root n sigma will be approximately z, which is the standard normal random variable, right? So that implies we can say summation I equal to 1 to n xi approximately root n sigma z plus n mu. Okay. Now here z is the standard normal random variable, and now this root n sigma z plus n mu follows the normal distribution with the mean parameter n mu and the variance parameter n sigma square. Because what is the expectation of root n sigma z plus n mu? It's going to be root n sigma expectation of z plus n mu, and expectation of z is 0, so it's going to be equal to n mu. And what will be variance of root n sigma z plus n mu? It's going to be root n sigma whole square variance of z. Okay, and variance of z equal to 1, so it's going to be n sigma square. That's why this root n sigma z plus n mu follows the normal distribution with the mean parameter n mu and the variance parameter n sigma square. Okay, that's why we can say the summation I equal to 1 to n xi will be approximately normal with the mean parameter n mu and the variance parameter n sigma square for a large n. Okay, fine. Normal approximation to binomial distribution. We know that computing probabilities involving binomial distribution will be computationally expensive when n is large. To get around this problem, earlier we used Poisson approximation to binomial distribution. But it makes sense only when n is large, p small, and np is of moderate size. Okay? Now we are going to look at normal approximation to binomial distribution. Let x be the binomial random variable with the parameters n and p. Then x can be realized as sum of n IID Bernoulli random variables with the probability of success p. That is, if x1, x2, so on, xn are IID Bernoulli random variable with the probability of success p, then the summation I equal to 1 to n xi will be binomial random variable with the parameters n and p. Because we know that sum of n independent Bernoulli random variable with the probability of success p will be binomial random variable with the parameters n and p. That's why this x can be realized as sum of this xi from I equal to 1 to n. Okay. Here expectation of xi equal to p and the variance of xi equal to p times 1 minus p for I equal to 1, 2, 3, so on. So here by central limit theorem, the summation I equal to 1 to n xi will be approximately normal with a mean parameter np and the variance parameter np times 1 minus p. Okay, so we can say that this x minus np by under root np times 1 minus p will be approximately standard normal. Fine. So when n is large, we know that this x will be approximately normal with the mean parameter np and the variance parameter np times 1 minus p. So if you want to deal with the probability of an events like this, that is probability of a less than or equal to x less than or equal to b, using this normal approximation, we can see that this probability will be approximately equal to phi of b minus np by under root np times 1 minus p minus phi of a minus np by under root np times 1 minus p, where this capital phi is CDF of standard normal distribution. Fine. This above result also referred as the De Mor's Laplace limit theorem. Fine. Okay. For p equal to 0.5, because of the symmetry, the shape of the binomial distribution looks bell-shaped. But if I let p to be very small, let's say p equal to 0.15, as you see, it gets skewed one side, right? But let us see what happens as I increase n. As you can see, as I increase n, the shape of the binomial distribution gets more and more close to bell shape, right? That's why for reasonably large n, this normal approximation to binomial distribution makes very good sense here, right? Normal approximation to Poisson distribution. Let x is a Poisson random variable with a rate parameter lambda, where lambda is a large number. Let us think like a lambda equal to n, where n is some positive integer. Then x can be seen as follows. X equal to summation I equal to 1 to n xi, where x1, x2, so on xn are IID Poisson random variable with a rate parameter 1. We know that sum of independent Poisson random variables again Poisson random variable. So the summation I equal to 1 to n xi will be again Poisson with the rate parameter 1 plus 1 plus so on 1 n times, that n is same as lambda. So I can say this is Poisson with a rate parameter lambda. Okay, that's why this x can be realized as summation I equal to 1 to n xn. Okay, here x1, x2, xn are Poisson random variable with a rate parameter 1. For the Poisson random variable, mean and variance both equal to rate parameter. So here the mu, that is expectation of xi, going to be equal to 1, and the variance sigma square, that is variance of xi, that also going to be 1. Okay, by central limits theorem we know that the summation I equal to 1 to n xi will be approximately normal with a mean parameter n mu and the variance parameter n sigma square. Okay, here n equal to lambda, mu equal to 1, sigma square equal to 1. So the summation I equal to 1 to n xi, okay, will be approximately normal with the mean parameter lambda, variance parameter lambda. Okay, that's why this x will be approximately normal with the mean parameter lambda, variance parameter lambda. So we can say that this x minus lambda by root lambda will be approximately standard normal. Fine. Okay. Normal approximation to chi-square distribution. A chi-square random variable with n degrees of freedom can be realized like this. Summation I equal to 1 to n xi, where x1, x2, so on xn are IID chi-square 1 random variables. Okay. We know that sum of independent chi-square random variables will be again chi-square random variable, where the degrees of freedom gets added up. So the summation I equal to 1 to n xi will be again chi-square random variable with the degrees of freedom 1 plus 1 plus so on 1 n times. Okay, so it will be chi-square random variable with n degrees of freedom. And here mu equal to expectation of xi, that equal to 1, and the variance sigma square equal to variance of xi, that equal to 2. Okay, so by central limit theorem we know that the summation I equal to 1 to n xi will be approximately normal with the mean parameter n mu and the variance parameter n sigma square. Here, so n mu going to be what? N times 1, that is n, and n sigma square is going to be what? N times 2, it's going to be 2n. So that's why this chi-square random variable with n degrees of freedom will be approximately normal with a mean parameter n, variance parameter 2n. Fine. Normal approximation to gamma distribution. Let x is a gamma random variable with a shape parameter alpha, rate parameter lambda. If alpha is a large number, let us think like alpha equal to n, where n is some positive integer, then x can be realized as follows. X equal to summation I equal to 1 to n xi, where x1, x2, so on xn are IID exponential random variables, because exponential random variable with a rate parameter lambda same as gamma random variable with the parameters 1 and lambda. Okay, we know that sum of independent gamma random variables with the same rate parameter lambda will be again gamma random variable where the shape parameters gets added up. So the summation I equal to 1 to n xi will be again gamma random variable with the shape parameter 1 plus 1 plus so on 1 n times, here n equal to alpha and the rate parameter is lambda. That's why this x can be realized as summation I equal to 1 to n xi, where this x1, x2, xn are IID exponential random variable with the rate parameter lambda. Here we know that mu, which is expectation xi, going to be 1 by lambda, and the variance sigma square, that is the variance of xi, going to be 1 by lambda square. Okay, and from central limit theorem we know that summation I equal to 1 to n xi will be approximately normal with the mean parameter n mu and the variance parameter n sigma square. Okay, here n equal to alpha, mu equal to 1 by lambda, sigma square equal to 1 by lambda square. So n mu will be alpha by lambda, n sigma square will be alpha by lambda square. So by central limit theorem, the summation I equal to 1 to n xi, that is x, will be approximately normal with a mean parameter alpha by lambda, variance parameter alpha by lambda square. Fine? Okay. Here I am trying to plot the PDF of the gamma distribution with the shape parameter alpha, rate parameter lambda is fixed to 1. The one you see here for alpha equal to 1. Now let me increase the shape parameter alpha. Let us see how the shape of the corresponding PDF changes. Fine? As you see, as we increase this alpha, the graph of the PDF gets more and more bell-shaped. That's why for reasonably large alpha, this normal approximation to gamma distribution makes very good sense here, right? The good thing about using these normal approximations to these distributions is to compute the probabilities involving normal distributions, we don't have to perform any computation. All we just have to do is just look up the standard normal table. That can be done in constant time. Whereas if you want to compute the probabilities involving distribution like a gamma distribution, you may have to do some expensive computation like doing some numerical integration and things like that. Okay, it may not be done in constant time. Note, we now have two possible approximations to binomial distribution. One is Poisson approximation, which is a good approximation when n is large, p small, and other one is normal approximation, which can be shown to be quite good when np times 1 minus p is large. The normal approximation will in general be quite good for values of n satisfying np times 1 minus p greater than or equal to 10. Fine? Okay. Problem. Let x be the number of times that a fair coin lands on heads in 40 flips. Find probability of x equal to 20 using normal approximation and then compare it to the exact solution. Okay. First of all, here x follows the binomial distribution with the parameters n equal to 40 and the probability of success p equal to 0.5. Here we are going to use normal approximation to binomial distribution. Please note that here x is a discrete random variable and we are trying to approximate with a continuous random variable. So if you directly use continuous distribution for probability of x equal to 20, answer will be 0. So it will not be useful. So that's why first we rewrite the event x equal to 20 like this. Because only integer in the interval 19.5 to 20.5 is x equal to 20. So these two will be equivalent. Okay. In general, the x equal to I event can be written like this. I minus 1 by 2 less than x less than I plus 1 by 2. Okay. This technique something called continuity correction. Then we use normal approximation to compute the probability of this event. Okay. First of all, here n equal to 40, p equal to 0.5. So np equal to 40 times 0.5, which is 20. np times 1 minus p is 40 times 0.5 times 1 minus 0.5. This is equal to 10. By central limit theorem, we know that x will be approximately normal with the mean parameter np, variance parameter np times 1 minus p. So, by central limits theorem, x will be approximately normal with the mean parameter 20 and the variance parameter 10. Fine? Okay. So first of all, x equal to 20 event we are writing as 19.5 less than x less than 20.5. Now we are trying to compute the probability of this event using normal approximation to binomial distribution. This look like a probability of a less than x less than b. So using normal approximation, we write this one as phi of b minus np by under root np times 1 minus p minus phi of a minus np by under root np times 1 minus p. Here the a role played by 19.5, b role played by 20.5 and np equal to 20 and np times 1 minus p equal to 10. So we have phi of 20.5 minus 20 by root 10 minus phi of 19.5 minus 20 by root 10. This gets simplified to 0.16. This gets simplified to minus 0.16. So we have phi of 0.16 minus phi of minus 0.16. This phi of minus 0.16 we can write 1 minus phi of 0.16 because phi of minus z we write as 1 minus phi of z, right? So now we have 2 times phi of 0.16 minus 1 Phi of 0.16 from standard normal table, it will be 0.5636. This whole thing gets simplified to 0.1272. So, using normal approximation to binomial distribution, the probability of x equal to 20 approximately 0.1272. Fine. Now, the exact probability using the PMF of the binomial distribution is 0.1254. As you can see, the approximate probability using the normal distribution is quite close to the exact probability of x equal to 20. Fine. Note, before we use normal approximation to discrete integer value random variable, we do something called continuity correction to the event of interest, so that probability of an event using normal approximation will be better. And we do this continuity correction only when we use normal approximation to discrete random variable, and we don't do this continuity correction when we use normal approximation to continuous type random variable. Okay, fine. Here is the continuity correction table. If x is a discrete random variable for which we are trying to use normal approximation, then event x equal to a, after continuity correction, we write as a minus 1 by 2 less than x less than a plus 1 by 2. And event x greater than a, after continuity correction, we write as x greater than a plus 1 by 2. For example, if I take a equal to 3, x greater than 3 will be equivalent to x greater than 3 plus 1 by 2, that is 3.5, because x greater than 3 means x can be 4, 5, 6 and so on. X greater than 3.5 means what? X can be 4, 5, 6 and so on. So these two events will be equivalent when x is a discrete random variable. That's why, so the probability of this event must be same as probability of this event. Okay. Similarly, x less than a event after continuity correction we write as x less than a minus 1 by 2, and x greater than or equal to a event after continuity correction we write as x greater than a minus 1 by 2, and x less than or equal to a event after continuity correction we write as x less than a plus 1 by 2, and a less than x less than b event after continuity correction we write as a plus 1 by 2 less than x less than b minus 1 by 2. Similarly, you look at these things. Okay, fine. Example, the ideal size of first year class at particular college is 150 students. The college, knowing from past experience that on the average only 30% of those accepted for admission will actually attend, uses a policy of approving applications of 450 students. Compute the probability that more than 150 of first year students attend this college. Okay, fine. Here, each of the 450 students who got approved may attend the college, that we call success, or not, that we call failure. Okay, independent to each other. If I let x denote the number of students that attend the college, that is x the number of success in sequence of 450 independent identical binary trials, each with a probability of success 0.3. The next follows the binomial distribution with the parameters n and p, where n equal to 450 and the probability of success p equal to 0.3. Then np equal to 135, and under root np times 1 minus p value will be 9.72. Here we are interested in the probability of x greater than 150. Okay, here we are going to use normal approximation to binomial distribution. Fine. Okay. Here n is large, so we are using normal approximation to binomial distribution. So the CDF of x at x, using the standard normal CDF, I can approximate like this. Phi of x minus 135 by 9.72. What is this 135? That is NP. This 9.72 is under root NP times 1 minus P. for n equal to 450, p equal to 0.3. Okay, fine. Now, first of all, our event of interest x greater than 150, after continuity correction it's going to be x greater than 150.5. Okay, now let us compute the probability of x greater than 150.5. This we can write 1 minus probability of x less than or equal to 150.5. So it's going to be 1 minus CDF of x at 150.5. Now using this approximation we can write fx of 150.5 as phi of 150.5 minus 135 by 9.72. This whole thing will be simplified to 1.59. So we have 1 minus phi of 1.59. Phi of 1.59 value from the standard normal table we can write 0.9441. This 1 minus 0.9441 value going to be 0.0559. Okay, fine. So the probability of x greater than 150 will be approximately 0.0559. So we can say that less than 6% of the time, more than 150 of the 450 accepted actually attend the college. Fine. Okay. Problem. Ram is standing on the number line at a position 0. He rolls a die repeatedly. If the roll is 1 or 2, it takes one step right, that is in positive direction. If the roll is 3, 4, 5 or 6, it takes 2 steps to the right. He always takes step to the right. Let Sn be the Ram's position after n rolls of the die. Estimate the probability that S90 is at least 160. Fine? Okay. Let me define sequence of random variables here. Let xi is the random variable which takes the value 1 if ith roll of a die shows up 1 or 2. 2 if ith roll of a die shows up 3, 4, 5 or 6. For I equal to 1, 2, 3, so on. Okay. Here, the sequence of random variables x1, x2, x3, so on, xn are IID random variables. Here, the probability of xi equal to 1 going to be same as probability of die landing on 1 or 2, that will be equal to 1 by 3. Probability of xi equal to 2 will be same as die landing on 3, 4, 5 or 6, that will be equal to 2 by 3. Fine. Now the mean mu, that is expectation xi equal to 1 times probability of xi equal to 1 plus 2 times probability of xi equal to 2, that is 1 times 1 by 3 plus 2 times 2 by 3, that is equal to 5 by 3. Okay, and expectation xi square going to be 1 square times probability of xi equal to 1 plus 2 square times probability of xi equal to 2, that will be 1 square times 1 by 3 plus 2 square times 2 by 3. It's going to be 1 plus 8 by 3, that is 3. Now the variance sigma square equal to variance of xi, that is expectation xi square minus expectation xi whole square. What is expectation xi square? We got 3 minus expectation xi whole square, that is going to be 5 by 3 whole square, that's going to be 3 minus 25 by 9, it's going to be 27 minus 25 by 9, that's going to be equal to 2 by 9. Okay, fine. Now Sn, which denote the Ram's position after n rolls of a die, can be expressed in terms of xi as follows. Sn equal to summation I equal to 1 to n xi. Here this x1, x2, so on, xn is sequence of IID random variables with the mean mu equal to 5 by 3 and the variance sigma square equal to 2 by 9. Okay. By central limit theorem, the summation I equal to 1 to n xi will be approximately normal with the mean parameter n mu, variance parameter n sigma square. For n equal to 90, this S90 will be approximately normal with the mean parameter 150 because n equal to 90 here, mu equal to 5 by 3. That implies n mu will be equal to what? 90 times 5 by 3. That will be equal to 150. And the variance parameter 20, that is n sigma square, right? So n sigma square going to be what? 90 times 2 by 9, it's going to be 20. Okay, so that's why this S90 will be approximately normal with the mean parameter 150 and the variance parameter 20. So the root n sigma going to be what? Root 20 value will be 4.4721. That's why the CDF of S90 at x is going to be phi of x minus 150 by 4.4721. It's like, phi of x minus n mu by root n sigma. Okay, fine. Now, we are interested in probability of S90 greater than or equal to 160. This event S90 greater than or equal to 160, after continuity correction I can write S90 greater than 159.5, and this probability of S90 greater than 159.5 we can write 1 minus probability of S90 less than or equal to 159.5, and this probability of S90 less than or equal to 159.5 we can write as CDF value of S90 at 159.5. Okay, so we have this 1 minus FS90 of 159.5, and the CDF value of S90 at x going to be approximately equal to phi of x minus 150 by 4.4721, as S90 is approximately normal with the mean parameter 150 and the variance parameter 20. So this 1 minus Fs90 of 159.5 will be approximately equal to 1 minus phi of 159.5 minus 150 by 4.4721. So this thing gets simplified to 2.12. So we have 1 minus phi of 2.12, and this phi of 2.12 value from the standard normal table we have this 0.9829. So this 1 minus 0.9829 simplified to 0.017. So this probability of S90 greater than or equal to 160 approximately 0.017. Fine. Okay. Now I am going to perform some simulations to verify law of large numbers and central limit theorem for random samples that come from 3 different probability distributions. Okay. Intuitively, law of large numbers says the following: if x1, x2, so on, xn be IID random variables, that is random sample, that come from the population having the mean mu, then for a large n, the sample mean 1 by n summation I equal to 1 to n xi will be approximately close to population mean. This is what intuitively law of large number says. On the other hand, central limit theorem says the following: if x1, x2, so on, xn be IID random variables having the mean mu and the variance sigma square, then the random variable, which is sum of x1, x2, xn, that is summation I equal to 1 to n xi, will have a probability distribution that is approximately normal with the mean parameter n mu and the variance parameter n sigma square. Okay. Now we are going to perform some simulations to verify these facts for the random samples that come from 3 different probability distributions. I am going to use uniform distribution, exponential distribution and Rayleigh distribution. Okay. First of all, this function uniform sample actually returns a random sample of size n that come from uniform distribution over the interval AB. But here A is fixed to 0, B is fixed to 1. So this function should return a random sample x1, x2, so on, xn that come from uniform distribution over the interval 0, 1. Okay, and this function returns random sample of size n that come from exponential distribution with a parameter lambda. What we do here, first we get random sample of size n that come from uniform distribution, then we transform the data using the transformation minus 1 by lambda log 1 minus u. We know this follows exponential distribution with a parameter lambda. So this transform data will come from the population that having the exponential distribution with a parameter lambda. Similarly, this function returns random sample of size n that come from Rayleigh distribution with a parameter b. Okay, first what we do here, first we get the random sample of size n that come from uniform distribution over the interval 0, 1. Then we transform that data using the transformation under root minus 2 by b log 1 minus u. We know this follows the Rayleigh distribution with a parameter b. So this transform data will be coming from population that having the Rayleigh distribution with a parameter b. Fine? Okay. What this LLN function does, it takes some sample like x1, x2, so on, xn, then returns numpy array which consisting of numbers like x1 by 1, x1 plus x2 by 2, x1 plus x2 plus x3 by 3. You get the idea. x1 plus x2 plus so on, xn by n. Okay, that's what it does. Next, what this LLN uniform does, first we are going to get the random sample of size n that come from uniform distribution over the interval 0, 1. That sample we are passing to this LLN function, so it will return this numpy array of this type for random sample of size n that come from uniform distribution. Fine. Similarly, this LLN exponential, what it does, first we get the random sample of size n that come from exponential distribution with a parameter lambda. Then we pass it to this LLN function, so it will return numpy of this type for exponential data. Similarly, same thing for this LLN Rayleigh. So what we do, first we get the random sample of size n that come from Rayleigh distribution with a parameter b. Then we pass it to this LLN function. So again, this function returns the numpy array of size n that consisting of numbers like this for data that come from Rayleigh distribution. Fine. Okay. Now let's look at the CLT uniform. Here we start with a empty list S. This loop runs capital N times. Here capital N we are taken 10,000. So this loop runs 10,000 times. Each time we are getting the random sample of size 100 that come from uniform distribution over the interval 0, 1. Then we sum it up and append it to S. So at the end, this function returns numpy array of size 10,000. It consisting of numbers that are sum of the random samples of size 100 that come from uniform distribution over the interval 0, 1. Fine. In the same way, the CLT exponential returns the numpy array of size 10,000 which consisting of numbers that are sums of random sample of size 100 that come from exponential distribution with a parameter lambda. Fine. Also, the CLT Rayleigh also do the same thing. It returns the numpy array of size 10,000 which consisting of numbers that are sum of the random sample of size 100 that come from Rayleigh distribution with a parameter p. Okay, fine. Now from this LLN functions, we have a numpy array of size 1000, which consisting of numbers like x1 by 1, x1 plus x2 by 2, x1 plus x2 plus x3 by 3, and so on, x1 plus x2 plus so on, xn by n. Okay, using these sample averages, we are going to plot the curve connecting these points I comma x1 plus x2 plus so on, xi by I. Okay, by law of large numbers, this curve should eventually stabilize at mean line. Okay, let's see if that happens. Okay, from the CLT functions, we got the numpy array of size 10,000, which are sum of random samples of size 100, 100 like that. Okay, now we are going to plot the histogram for these data points. So according to CLT, that histogram should be bell shaped. Okay, let me run this. This is the law of large numbers for random sample that come from uniform distribution over the interval 0, 1. As you can see, this curve eventually stabilizes at mean line. Here A equal to 0, B equal to 1. So the mean going to be A plus B by 2, that is half. So this is the mean line. Okay, mu equal to half. Okay. As you can see, as n gets bigger and bigger, this x1 plus x2 plus so on xn by n will be close to this population mean mu. Okay, as you can see, this curve stabilizes at this green line, which is a mean line. Similar thing happens for random sample that come from exponential distribution, also for random sample that come from Rayleigh distribution. Okay. See, these curves are stabilizing at the mean line for corresponding distribution. Here we are looking at the central limit theorem for uniform distribution. What we did here, we got the 10,000 data points that are sums of the random sample of size 100 that come from uniform distribution over the interval 0, 1. Then we plotted histogram. As you can see, this histogram shape is bell shaped, so we can say that the sum of the random variables I equal to 1 to 100 xi is approximately normal. Okay, here also what we did, we got the numpy array of size 10,000, which consisting of numbers that are sums of the random samples of size 100 that come from exponential distribution with the parameter lambda. That lambda I have taken, I think 2 or 3 something. Again, you can see this histogram shape is again bell shaped, so we can say that the summation I equal to 1 to 100 xi is approximately normal. Okay, similar thing happens for the random samples that come from Rayleigh distribution. Fine. Looking at these simulations, we can feel these results, law of large numbers and central limits theorem intuitively, right? Okay. Now let me stop. Thank you.